Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating paper titled Discovering Chunks in Neural Embeddings for Interpretability.
Sounds intriguing. I've been hearing a lot about interpretability challenges in deep learning lately. Anything that sheds light on how these networks are actually processing information is definitely welcome.
Interpretability is key. We can't just keep building these black boxes and hoping for the best. We need to understand what they're doing, especially as they get deployed in critical applications.
Exactly. It's not just about performance, it's about trust. If we don't understand why an AI makes a certain decision, how can we trust it? Especially when it comes to high-stakes situations.
Okay, so the core idea of this paper is that neural embeddings, which are those dense vector representations that neural networks learn, often contain chunks, these sort of meaningful reusable patterns of activation.
Right, like building blocks of knowledge in a way.
Precisely. The authors propose a method to automatically discover these chunks, and then use them to explain what the network is doing. The idea is that by decomposing these high-dimensional embedding vectors into meaningful chunks, we can gain insight into the internal representations of the neural network.
So they're trying to move beyond just looking at individual neurons and instead focus on patterns of activation across multiple neurons. Because just looking at individual neurons firing doesn't tell you much of anything.
Well, I think that's the problem, right? That neurons on their own, especially in these huge models, are almost meaningless without understanding the context of the other neurons they're connected to. This idea of chunks is actually brilliant. I wonder how they actually implement it.
They use a technique that involves clustering the embedding vectors. Basically, they try to find groups of vectors that are similar to each other, and then they treat each of these clusters as a chunk. Then, they see how these chunks are activated in response to different inputs.
Clustering, huh? So it's a way of finding common patterns in the activation space. Interesting. It's like trying to find recurring motifs in a complex tapestry. The thing is, what metric do they use to determine similarity?
Yeah, the similarity metric is crucial here. I mean, you could use cosine similarity, Euclidean distance, but depending on the specific application, one might work better than the other. Do they talk about that in the paper?
They experiment with a few different distance metrics, and they also use some dimensionality reduction techniques, like PCA, to make the clustering more efficient.
PCA makes sense to get rid of some of the noise and focus on the most important dimensions, but I'm still a bit skeptical about whether this can really give us meaningful insights. Are these chunks actually representing anything concrete, or are they just statistical artifacts of the training data?
That's always the question, isn't it? Are we uncovering genuine understanding or just sophisticated memorization? But if these chunks are consistently activated in response to specific types of inputs, that suggests they're capturing something real about the underlying data distribution, right?
Maybe. But it also depends on the task. If you're training a network to classify images of cats and dogs, these chunks might just be capturing low-level features like edges and textures. It's not clear how this would generalize to more complex reasoning tasks.
That's a fair point. The authors do evaluate their method on a few different tasks, including natural language processing and image recognition. And they show that the chunks they discover can be used to improve the interpretability of the network's predictions. For example, they can identify which chunks are most relevant for a particular input, and then use those chunks to explain why the network made that prediction.
Okay, that's interesting. So it's not just about finding the chunks, it's about using them to provide explanations. Can you give me a more concrete example of that? Like, how does it work in practice?
Sure. Imagine you have a sentiment analysis model that's trained to classify movie reviews as positive or negative. Using this chunking method, you might find a chunk that's consistently activated when the model encounters words like amazing, fantastic, and wonderful. Then, if the model predicts that a particular review is positive, you can point to this chunk and say, the model is predicting this review is positive because it contains words that activate this positive sentiment chunk.
Okay, I see. So it's like identifying the key features that are driving the model's decision. But still, I worry that this is just a surface-level explanation. It doesn't really tell us why those words are associated with positive sentiment, or how the model is actually reasoning about the meaning of the review.
Right. It's more like identifying correlations than understanding causation. The model might be picking up on spurious patterns in the data that don't actually reflect the underlying sentiment. For instance, it could be that positive reviews happen to contain more exclamation points, and the model is simply learning to associate exclamation points with positive sentiment.
But even if it's just correlations, that's still valuable information, right? I mean, it gives us a way to debug the model and identify potential biases. If we see that the model is relying on spurious features, we can try to correct that by adding more data or modifying the training process. It does help make the black box a little bit clearer, even if we can't see completely inside.
Exactly. And the authors argue that this method can be used to improve the robustness of the model. By identifying these chunks, we can potentially make the model less sensitive to adversarial attacks or noisy data, because it's looking at the bigger picture rather than just getting tripped up by specifics.
I suppose, but I still think we need to be careful about overinterpreting these chunks. Just because we can assign a label to a chunk doesn't mean that the model is actually using that chunk in the way we think it is. I mean, are we projecting our human understanding onto something that's just a bunch of numbers?
That's a valid concern. It's like looking at a Rorschach ink blot. We see what we want to see. We need to be rigorous in how we validate these interpretations. Maybe we can use techniques from neuroscience to compare these chunks to the activity patterns in the brain.
That's an interesting idea. See if there's some sort of correspondence between the AI chunks and the way the brain processes similar information. A biologically inspired approach might be useful. How cool would it be to map AI thoughts to actual human thoughts?
Yeah, I'm all for biologically inspired AI. The idea of knowledge networks as dynamically interacting structures aligns well with theories of neuroplasticity. This could lead to AI systems that aren't just reactive, but can learn and adapt like the human brain. This also makes me think about self-organizing neural systems. What role will synaptic plasticity play in their development? How do you get these networks to actually learn from mistakes?
That makes me think about measuring the emergence of agency. Are there quantitative metrics that can track decision-making capabilities from complex interactions within the network?
I'm still stuck on the symbolic reasoning. How does this agentic aspect manifest in the reasoning process? Is it a form of rule-based reasoning, or is it just an emergent property from learned relationships? I suspect the ability to act within the graph is limited by the underlying symbolic system.
If this agentic approach translates between different coordinate systems, wouldn't that require some form of symbolic reasoning? That would alleviate my concern about deep learning being brute force.
Speaking of which, this whole discussion reminds me of the research around intuitive physics understanding in AI. There's some interesting work being done using self-supervised learning to train models that can predict how objects will behave in the real world. It's fascinating that this can be done without explicitly programming in the laws of physics.
Oh yeah, I've seen that. If these models are pattern matching, can we separate that from memorization? Is intuitive just a human-centric judgment?
I'm skeptical. Deep learning's ability to grasp the why behind phenomena seems limited to surface-level correlations. A statistical approach can predict, but not provide understanding.
That's where coordinate systems come into play. The key to AGI isn't just data crunching, but understanding how different coordinate systems interact. Current deep learning feels like brute forcing.
Absolutely. That's a fascinating connection. It's almost like the AI is developing its own internal model of the world based on the patterns it observes in the data. And that model can then be used to make predictions about future events.
But how robust is that model? If you change the environment slightly, will the model still be able to make accurate predictions? Or will it fall apart because it's only learned to memorize the specific conditions it was trained on?
That's the million-dollar question. And it gets to the heart of the problem with current AI systems. They're often very brittle and don't generalize well to new situations. That's why we need to move beyond just pattern recognition and start building systems that can actually reason about the world.
Right, and that's where the idea of chunks comes in again. If we can identify the reusable building blocks of knowledge, we can potentially create AI systems that are more flexible and adaptable. Systems that can combine these chunks in novel ways to solve new problems.
So, almost like a kind of modular AI architecture, where you have these pre-trained chunks that can be plugged together to create different types of intelligent behavior.
That sounds a lot like symbolic AI, where you have predefined rules and representations that are used to reason about the world. The difference is that, in this case, the rules and representations are learned from data, rather than being explicitly programmed.
Exactly. It's a hybrid approach that combines the best of both worlds. You get the flexibility and adaptability of neural networks with the interpretability and explainability of symbolic AI. That's what I mean by translation between coordinate systems. We need both.
Which brings us back to the paper. It presents a promising approach to making deep learning models more interpretable. By discovering these chunks, we can gain a better understanding of how these networks are processing information, and hopefully build more robust and reliable AI systems. The concept of deep graph reasoning combined with self-organization resonates with me. The key to AGI might lie in biologically inspired methodologies.
And it hints at a solution to the black box problem. By mapping knowledge onto graphs, we might understand how the AI processes information. The exponential growth of data combined with deep learning is paving the way toward AGI.
I'm still concerned that the deep part is overshadowing the symbolic reasoning component. It feels like a workaround. We need to be careful about replicating human intelligence without understanding core mechanisms.
I wonder if the agentic aspect involves different coordinate systems, like our brain handles different sensory inputs. We need more than just pattern recognition. We need algorithms that understand relationships in time and space.
So, where do we go from here? What are some promising directions for future research?
Well, I think one important area is to develop better methods for evaluating the quality of these chunks. How can we be sure that they're actually representing meaningful concepts and not just statistical noise? We need to develop metrics that can measure the semantic coherence and the explanatory power of these chunks.
I agree. And I think we need to explore ways to integrate these chunks with symbolic reasoning systems. How can we use these learned representations to build more powerful and flexible AI systems that can actually reason about the world? Could we build a system that uses chunks to generate symbolic rules, or that use symbolic rules to guide the discovery of chunks?
From my perspective, the key is to focus on spatiotemporal reasoning. How can we design AI systems that can understand and reason about the relationships between objects in space and time? And how can we use these chunks to build models of the world that are more grounded in reality? I think we need algorithms that can translate between different coordinate representations.
And I think we need to look more closely at the brain for inspiration. How does the brain represent and process knowledge? Can we learn anything from the way the brain organizes its neural networks that can help us build more intelligent AI systems? If these networks truly emulate self-organizing neural systems, what role will synaptic plasticity play in their development?
A biologically plausible path to general intelligence. I think we also need to figure out how to scale these methods to larger and more complex models. Can we discover chunks in the massive language models that are being trained today? And can we use those chunks to make those models more interpretable and controllable?
Right. And we need to address the ethical implications of these technologies. As AI systems become more powerful, it's important to ensure that they're used responsibly and that they don't perpetuate biases or discriminate against certain groups. Ensuring understanding will be crucial to ensuring ethical considerations.
And we need to be mindful of the potential for these technologies to be used for malicious purposes. As AI systems become more sophisticated, it's important to develop safeguards to prevent them from being used to create autonomous weapons or to spread disinformation. It's a matter of national security.
Absolutely. It's a complex and multifaceted challenge, but I'm optimistic that we can make progress towards building more intelligent, interpretable, and ethical AI systems. It's intriguing that this method doesn't require explicit physics rules as input, but rather relies on patterns in data. Could this approach pave the way for more robust, adaptable intelligent agents?
I'm still a believer in deep learning's potential. Self-supervised pre-training on physics data presents a fascinating path forward. If we can achieve comprehension through statistical methods, it opens the door to a wider range of data-driven approaches.
I remain wary. The current research sidesteps explicit representations and symbolic reasoning. Can we combine statistical learning with symbolic knowledge representation for a more robust path?
If intuitive physics understanding emerges from self-supervised pre-training, then a crucial aspect of AGI might be the ability to learn the translation between different coordinate systems. Purely brute force deep learning isn't elegant enough.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion insightful. Until next time, keep exploring.